Okay, hello everybody. Welcome back again. I'm going to jump ahead a little bit here to chapter 3.3, and I'm going to talk about, in particular, the addition rule. We're going to focus for a second on probabilities that have the word or in them. So if I have two events, A and B, then I can consider what's the probability that either A or B or both of these things happens in a trial of my probability experiment. So for example, I could ask you what's the probability that I pull a queen when I take one card out of a deck, and I can also ask you what's the probability that I pull a heart. Or maybe I'm concerned with either of these events happening. Maybe I'm concerned if I pull a queen or a heart or both. I could pull both. I could pull the queen of heart, which would satisfy both of these rules, right? So what that is the probability that A or B occurs. And of course, an important idea in mathematics is that this or does mean both. Sometimes in English, when I say or, I don't mean both. If I say I want either Steve or Jamie to come with me, it's almost implied that I don't want both of them to come with me. But in mathematics, when we use the word or, we mean that both is okay. So if I ask you what's the probability that it will rain or snow tomorrow, if it somehow both rains and snows, then that's okay. I want to include that in my event. And so when we do find a probability like the probability of A or B, we need to be careful and not jump too quickly into just calculating things. So let's think about this example here. It's a nice example. Let's suppose that there's 985 traffic fatalities last year in a particular town, and we know that 138 of them, the driver of the vehicle was intoxicated. And in 325 of these accidents, that's a lot. Where is this town that so many people are intoxicated? In 325 of these accidents, the pedestrian was intoxicated. So my question is, given just this information, do you think you can tell me the probability that out of these 985 events, do you think you can tell me what the probability that either the pedestrian or the driver was intoxicated? Think about it for a minute and see if you can answer that. And if not, tell me why you can't answer it. So what did you think? Well, let me slow down for a minute and let me think about this a little bit more. So let's think about the experiment where I randomly pick one of these fatalities. There's 985 of them. And let's let A be the event that the pedestrian was intoxicated. Well, based on what we just said, we know that 325 of those accidents involved intoxicated pedestrians. So the probability that a pedestrian was drunk in my traffic accidents was 33%. 325 over 985 comes out to about 33. And if I let B be the event that the driver was intoxicated, then the probability that B happens is, well, how many drivers were intoxicated? I had 138 out of 985. So that gives me about a 14% chance that the driver was intoxicated. So what's the probability that either the driver or the pedestrian was intoxicated? Now, you might be tempted to say, well, 33% of the time the pedestrian was drunk, 14% of the time the driver was drunk. So the probability that either of them was drunk was probably 33 plus 14 is 47. But is this right? Do you think it's true that 47% of the time somebody was drunk? And why not? If you disagree. Well, what do we think? What do we think? Well, here's the problem. The answer is no. It's incorrect to assume this. Is it correct? No, it's not correct. And here's the real reason. These 325 accidents include every time a pedestrian was drunk. And these 138 include every time a driver was drunk. But what if both the pedestrian and the driver were drunk? What if both of them were intoxicated during an accident? Then, when I came down here and I attempted to count this number on the top, don't just add things without understanding what you're adding. When you're adding this numerator, you're trying to count up the total number of times that either the driver or pedestrian was intoxicated. And when you took this to be your count, you added the times when the pedestrian and driver were both drunk twice, because this one occurrence occurred here in these 325 cases. And you also counted it here when the driver was drunk. For example, here's the table that shows the total breakdown of all cases where driver and pedestrian were drunk. The way I read this is saying, well, where did that 325 come from? Those were all the cases where the pedestrian was drunk. 59 times the driver and pedestrian were drunk, and 266 times only the pedestrian was drunk. But look, 59 times they were both intoxicated. So if I gave you only this table, and I said, well, here's a listing of 985 accidents, I want you to count up the number of times that either the driver or pedestrian was intoxicated. How would you do that based on only this table? Well, of course, you would say, well, let me count all the cases where the driver or the pedestrian was drunk. In these 59 times, yeah, somebody was drunk. In fact, they were both drunk. In these 79 times, the driver was drunk. And in these 266 times, the pedestrian was drunk. The times when nobody was drunk, these are down here, 581 times. So if I add up 266 plus 79 plus 59, I get 404. So the probability that either pedestrian drunk or driver drunk is 404 out of 985. This differs from this number. This number is always bigger. It's too big because we've counted things twice. The only time that it would be equal, well, the only time we can actually do this is when if this number was actually 0. We'll talk about that more in a minute. So, to find the probability of A or B, we can't just add up the probability of A and the probability of B. It actually happens that only 41% of the time was somebody intoxicated, either the driver or a pedestrian. And so, in general, to find the probability of A or B, there's a nice little formula we can use. Notice that we could have done this a few ways. The way that we just did it a minute ago is the way when we sort of have this table staring at us in the face. We take the probability of, let's see, A and B occurring. That's the probability that both people are drunk. And we add it to these probabilities, the probability that one was drunk and the other wasn't, and the probability that the other was drunk and the other was not. And we add these total number of cases up to find the size of our event space here. But another way we could have done it is we could have taken the probabilities that we knew. Remember, we knew that we had 138 cases of driver intoxication. That's the sum of these two numbers here. And we could have taken our number of cases of pedestrian intoxication, which is the sum of these two numbers here. But notice that if I did that, 138 plus 325, what I'm really doing is I'm saying, okay, let me take 59 plus 79, that's my 138, plus 59 plus 266. And what does that give me? Look, I added 59 twice. Because when I add up the probability the driver was drunk with the probability the pedestrian was drunk, I add this number 59 twice. So I would have had to subtract one of these 59s to actually get the right number of cases. So the idea is that when we add up these probabilities, we have to make sure that we're not counting any outcome twice. And this gives us the addition rule, this basic idea that we just said. In general, if I wanted to find the probability that either A or B happens, one way that I can do it is I can take the probability of A, the probability the driver is drunk, the probability of B, in our example, the probability the pedestrian was drunk, and then subtract the likelihood that they both happened. And the reason that we're doing that is because we actually count this number twice instead of just once. So this is what the addition rule in probability says. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And so to illustrate this, let's just do one quick example here. Let's do this example actually. And so if I toss a single die, try this question down here. What's the probability that an even number or a number less than 3 comes up. So I want you to try this two ways. Way number one, I want you to try thinking about it intuitively before you actually go ahead and apply this rule. Try to think about what this really means. This isn't a hard question if you can understand it. If I throw a die, what's the probability that an even number or a number less than 3 comes up? Answer it first using common sense. And then go ahead and try to use the probability rule, addition rule here. Let's see if you can do that. I'll take it up in 1 second. Okay, so first the common sense approach. So here I'm only throwing one die, so of course I can think about my sample space as being any of the 6 outcomes that I get when I throw a die. I can get a 1, 2, 3, 4, 5, or 6. And so my first event here, I can call this A. The probability that I throw an even number, well, what's this event space? And the even numbers are 2, 4, and 6. So I say what's the probability of just throwing an even number? It would be 3 out of 6. The probability that I throw a number less than 3, I'll call this event B. What are the numbers less than 3? That's 1 and 2, of course. And so what's the probability that I do either of these things? What's the probability that either something in here happens or something in here happens? Well, how can that happen? Of course, the list of all possible outcomes, I could either have a 1, that's from this space, a 2, that's the number that's in both of these, a 4, or a 6. So how many ways can this happen down here? This is A or B. Either an even number or a number less than 3. There's 4 ways out of my original 6. So the answer to this question is 4 out of 6 or 2 out of 3, which is 66.7%. Okay, so let's go ahead and keep the same example. Let's just verify this addition rule here just for fun. So to use the addition rule in this case to find the probability of A or B, I need 3 numbers. I need to know the probability of A, the probability of B, and the probability of A and B. And so letting A denote the event where I toss a die and I get an even number, we know the probability of A is 3 over 6. Letting B denote the event that I throw a number less than 3, the probability of B is 2 over 6. And what's the probability of A and B occurring? So what does that mean? That means that both of these things happen. In other words, I get an even number, which means I get a 2, 4, or 6, but I also get a number less than 3. And so how many ways can I have overlap between these two sets? Of course, there's only one even number that's less than 3, and that would be 2. So the probability of A and B is equal to 1 out of 6. This is my event space. I only have one event, one outcome in my event, and that's throwing a 2, and of course I have my original 6 outcomes. So the probability of A and B is 1 over 6. So what does the addition rule say? Again, forgive my terrible handwriting. It says that if I want to find the probability of A or B, then what I do is I take the probability of A, and what's that? 3 over 6. That's the probability of throwing an even number. I add the probability of throwing a number less than 3, which is 2 over 6, and I subtract the probability of throwing both an even number and a number less than 3, which is 1 over 6. 3 plus 2 minus 1 gives me 4 over 6, or 2/3. And of course, that's the same number that we found using our intuitive approach. So this is the addition rule. It's a law that holds for any events A and B in a probability space. I can find the likelihood of A or B by applying this formula. And of course, another thing to note is that a simple rearrangement of this formula allows me to find the probability of A and B as well. I can just bring this to this side, and I can use this same idea to find the probability. If I know the probability of A, the probability of B, and the probability of A or B, for instance, I can use the same formula to find the probability of A and B. That's it for now. I'll talk about mutually exclusive events next.